Hi, I'm Luca. I'm a Google developer expert, and today I'm here to talk to you about deep learning, which is a quite intermediate advanced topic. So before starting, I would like to ask you if any of you had any experience with machine learning. Okay, that's not bad. And with TensorFlow, maybe? Okay, that's one. That's great. So I hope you will enjoy the talk, and even if it's a bit technical, I hope it can give you inspiration about how to use this new technology. So time to start. And I'm going to tell you today, first of all, about deep neural networks, DNN, for tabular data. What does it mean to try to solve a problem involving data which is on a table, basically a matrix? We will explore how to deal with a data pipeline. We will talk about cross-validation, which is a very important topic in machine learning, but usually when you do deep learning, you never do cross-validation. I will show you a working example, very briefly, but you can find a link and you can try to rehearse all the code at home and even run the code. And then finally, I will give you motivation why to use deep neural networks for a problem like tabular data, which may sound to you a little bit overkill maybe. Since not everyone knows about machine learning and deep learning, I will try to give you a brief recap, brief idea of what we are talking about. Deep learning is a subset of machine learning. So we are talking about a set of technologies or solutions which are part of machine learning. And machine learning itself is part of AI, artificial intelligence. You will often hear them mingled together. Someone will tell you that machine learning is AI and so on. But actually remember, it's just a technique. It's just a way to solve problems that involve that you put intelligence into your automation. So machine learning and deep learning are a part of artificial intelligence. And you often don't see them used everywhere. So I'm not telling you a kind of free lunch. There's no free lunch really. To go more in depth, I will help you to have an idea exactly how a deep neural network is made and exactly what this kind of technology is working. Showing to you this playground. You can find it on the website, the TensorFlow, the Google library for deep learning. And you can see it's actually a stack of computational units. How are they stacked? In the form of a graph. At one hand, you have your input. You have your data that enters inside this graph, which is a cyclic. So it just goes forwards. And we are structured into layers. Into each layer, something happens. All the input signals, they enter, they are weighted, and then they are transformed using a transformation function. Sometimes it's just a linear function, so it's just transmission of a signal. Sometimes it's non-linear, so something happens that create, for example, cubes instead of lines, and your signals become richer. In this case, you see there are about 5 layers, and what's the purpose of this deep neural network? Is to figure out the function for a spiral. And how does it achieve that? By looking at a graphical example. You have points plotted into a Cartesian space, and they are in the shape of a spiral, and the data flowing through this graph provides the information to the deep neural networks to figure out a function that can approximate. The function sometimes is not perfect. It really depends on the example you are feeding your network with, if it is good data or bad data. But here the data is quite clear, and in the end it figures out a way to divide the spiral into the points which are in blue and the points which are in pink. You may wonder, why is it relevant? Well, if you are here, maybe you have heard that actually this is a new approach to do software development. For many years, we have tried to face problems such as image recognition, for example, facial recognition, how to recognize a person from a photo using features we created and made. We look at many photos, we try to figure out what kind of information an algorithm, very simple or a little bit more complex, could be helped in detecting if the photo is yours or of your friends. Deep neural networks, deep learning, help you to achieve that without explicitly programming anything like that, just by providing examples. So you pose your problem as a data problem. You provide the correct examples for your problem to be solved. For example, you provide many faces with their label, so the names attached to them, and you propose the digitized images to the neural network, and the neural network, if it is correctly built, will provide to you exactly what you want, the answer, and you don't have to program anything. Don't think it's an easy way, even if there are very cool tools like AutoML. Often it is something you will need a certain effort. And so by a certain effort, we already had very great advances using this technology. We are almost going to have self-driving cars which can see and perceive their environment through deep neural networks, and they can, of course, use that information in their driving behavioral system, just fusing a lot of information from sensors and vision. Deep learning in healthcare, because now we can detect with the same experience of well-seasoned doctors the probability, the possibility that you are healed by analyzing X-rays and tomography using deep learning. You have deep learning in search engines. Just recent news that Google is using a neural network called BERT in order to provide more sensible and more correct answer to queries. You have deep learning, voice search and voice activity assistance, in automatic machine translation, in sophisticated recommender system that can figure out exactly what your tastes are and can suggest you the right product to buy, and also in image generation recognition, which is really revolutionizing the way we are imagining the future of, for example, television, of videos and so on. Maybe you heard about deep fakes. Is an application which has, of course, sometimes discutable use, that actually can stick your face into the face of a person in a video. So you can become Obama, you can become your famous actor, and that's very cool. But, okay, up to now sounds really great, but when you go and see inside your business, inside your problems, you cannot find this so great data that, created so fantastic POCs, so fantastic proof of concepts that we talked before. Actually, when you go and see your data, it's just tabular data. What does it mean? You go, you find a data set. Inside your data set, you have many tables, and you can join the tables and pick up something reasonable about your business, your problem. And all this data actually is not exactly what you are told about when you start applying deep learning. In fact, there are some challenges. First of all, imaging. You are going into a database, you can find everything you may figure out of. You have text, you may have images, but very little usually. You have a lot of numbers, you have, kind of ordinals, you have dates, an incredible mess. And often the data is dirty, but we will talk more about that later. Now, let's just figure out it's mixed and very complex. You have sparse data. What does it mean? It means that you have fields that actually contains very few examples. For example, you have your ID customers, and even if it is a reasonably important customer in your database, you cannot figure out to have the same density of information that you can find in an image, where each pixel will provide to you for each of the 3 channels some number you can use. And deep neural network actually struggles with sparse data because it works using a principle called backpropagation, which actually is a little bit ineffective if your data is just made of 1 and zeros. And then you don't have fantastic best practices, the state-of-the-art networks that you can find in image and text problems. These networks are really pre-trained. For example, you want to find a dog in your picture, okay, we already know what is a dog. You want to find an hamburger or a hot dog, okay, maybe they don't know, but it's easy for them to be just, fine-tuned to even find that information for you. You actually don't have anything like that in tabular data. You are just in an unknown territory. You have often less data. Some databases are very large, but commonly you won't find the same amount of images or the same amount of text that you have in the best practices that books are telling you. And also, you have to face a big problem. You have competitors, very strong competitors from classical machine learning algorithms. 80% of the world, what is called AI, is running on linear regression and logistic regression. They actually will work. For some problems, they really work. And a lot of business people will tell you, oh wow, we really cannot understand what's that. It is really a dark box. There are a lot of nodes, a lot of connections. I really cannot figure out what's that. So you have a lot of challenges, but don't desperate. The challenges are serious, and so are the opportunities. Andrew Yang just recently stated, deep learning has seen tremendous adoption in consumer internet companies with a huge number of users and vast big data, of course. But for it to break into other industries, for it to become a common technology in everyday life, where dataset sizes are smaller, we now need better techniques for small data. And actually, this is exactly the topic of today. I'm just to show to you the tricks, the tips, and the approach you should take for this kind of problems. It takes some efforts, so don't expect anything automated or very easy to be done, but you don't need to reinvent the wheel, because you have TensorFlow, this library provided by Google, specialized on deep learning. You have Keras, which is another project recently incorporated into TensorFlow 2.0 as a high-level API for TensorFlow, and you have a couple of very useful packages from the Python world. One is called scikit-learn, and it's for classical machine learning. Another one is pandas, used in the financial sector for manipulating data. If you can use all these together, you will achieve for sure your results, because they help you to process your pipeline according to your inputs, that is their types, so you just segment your data, and after that, I will show you how to create a suitable neural network architecture to face such kind of problems. Of course, if you have any knowledge of your problem, it is a prior knowledge. Classically, it's called feature engineering. It's not bad to put that also. But deep learning can give you a huge boost anyway. And then I will show you how to tune and test your solution using cross-validation. So first of all, use the right tools, Keras and scikit-learn. In particular, scikit-learn has a peculiarity that is very interesting as a method of approach for these problems. It has the method of fit, transform, and predict. What does it mean? It means since you are working on examples, once you are done with your examples and your solution has learned from examples, you have to actually reapply everything to new data. And using these methods, it's much, much easier. And let's now dive into the data pipeline, and we show to you how it works. We start with numerical variables, we talk about dates, and then we just deal with the biggest and most troublesome data of all, the categorical one. Numeric data. When you have numeric data, it seems quite an easy job, a piece of cake, right? Everything is numbers, you just have to feed the numbers into the neural network. Well, that's not really true. First of all, you have to trash all the low variance variables. What does it mean? You have many fields in your tabular data. Some fields do vary very little. They have too many missingness. They just, record something very niche, very peculiar of certain situations. There's very little variation. Deep neural networks can really struggle with such kind of information. You have to just leave them apart. Then you have missing values. We find out that null is the most frequent value in your data, and that's happened quite often. So our neural network won't do anything with such a value, which is a known value. You have to provide something in substitution to that. And the usual approach is to use the mean or to use the median. The median actually is a smarter strategy because it doesn't need for your data to be Gaussian, to be normal. So you just don't care, just use the median. But another very important thing that you don't have to forget is that neural networks have many computational units, have a very complex architecture. They can figure out things that maybe are overlooked by you when you look at your data. So they can figure out if there is any pattern in your missing data. Because sometimes the fact that you are missing an information is an information itself. So you create many variables called missing indicators that tell you if in a certain variable a value is missing. And it's just, 0 and 1s. Then you have to strive to make your data more Gaussian-like. Please don't laugh, but it's something that works. Even it is very old-fashioned statistical rule. And you have to catch outliers. Outliers are the very strange numbers that you can find in your data. They happen because maybe they are very rare individuals or events that can happen. Sometimes, more often, they are errors. And you can catch them by, first of all, filtering your data or inside your network using a layer called batch normalization. And we'll talk more about that also later. And then finally, normalize all the data. What does it mean? It means that your data, ideally for your neural network, should have zero mean, so be centered, and have as small as possible standard deviation. Usually if you do statistical normalization, you can have achieved that. So your neural network can learn faster and have numeric inputs that it can handle in an easy way. That's a lot of information, right? A lot of prescription. I guess you are wondering now, how can we do that? Wow. Well, just use scikit-learn. You have so many very useful and easy to use functions. The first one is variance threshold. You just call it, you fit on the data, and then you can transform your data. And what does it for you? It just filters out all the low variance information. So we just trash away all the unuseful variables. And then you have to impute missing values, right? You have another function called simple imputer. All these functions are not in TensorFlow, and actually TensorFlow doesn't have this kind of facilities because it was thought for different problems, for problems of image, of sound, of text, not problems that you can find with tabular data. With simple imputer, it will just transform your missing data into what you want the most, median, I hope, and it can also automatically create your indicators variables, telling you if a certain variable has a missing value in it. Also, I told you that you should try to make your data Gaussian-like, right? Wow, that's terrible. You are really figuring yourself, looking at your data and trying to achieve a way to do that. But scikit-learn provides two very convenient functions. One is power transformer, which is actually a statistical transformer. It's based on the Box-Cox transformation, which is quite efficient in turning something like you can see on your left, so a distribution which is very skewed, into something more normal like what you see on your right. But if you are not satisfied with that and can assure that there's better than what you have seen up to now, you can use another function called quantile transformer, which will force all your data to be normal. And for example, you can see that in the transformation on your right, it already figured out that there is a core, a mass of very common numeric information in this variable, and there are two extremes. So you really can point out to the neural network what are very rare, very strange numbers in its opinion, in its, of course, processing of data. And then finally, before feeding everything inside your neural network, you have to standardize it, right? And you have two choices, standard scalar and robust scalar. They both will center the data to 0 mean, and will give you a variance which is reasonable according to the spreading of your variable. Standard scalar is the classical one, so just remove the mean and divide by the standard deviation. The robust scalar instead is based on quantiles and is more robust to outliers. So if you fear that you don't have all your data all right, there are some strange numbers, the robust scalar will just put them, of course, at the extremities, but the extremities won't be too far. And that's much better for your neural network. Now we're going to talk about dates, and dates are another big problem, right? Because they're written in so many different ways, and actually they contain a lot of information, because from a single date you can extract the year, the month, the week, the day of the year, the day of the month, and the day of the week. And each of these could be important for your neural network to work properly and figure out the prediction you desire. But also, you have to mark special days, especially holidays, or particular periods according to the problem you're going to solve. If you're going to sell jewels, for example, St. Valentine is a very important date, even if it's just an holiday. And also, you can figure out that time is continuous, so you're just providing the time from 0 to 24, but actually 24 is very near to 0, to 1, and so on. And how can you represent it? Using trigonometric transformation, using sine and cosine transformations. Is it difficult? No, it isn't, because you use pandas. You transform everything into a type, which is date times 64, and then this type can extract for you by methods all the information you need. And also, it can help you to transform very easily, because it can extract for you the right information by trigonometry, all your continuous data, continuous time, into a cyclic time value. And that's much better for your neural network to handle. So we arrive. I hope I didn't run too much, but I know the time is very little and the information is much. Actually, I will make this presentation public. I also write a Medium article about that, so don't worry, you will have it for sure. Categorical data. Well, we start from the easiest type of categorical one. It's the ordinal one. So ordinal, it means it has an order. For example, it just, we just talk about time, so the days of the weeks have an order, right? But you call them lunedì, martedì, so Monday, Tuesday, Wednesday, and so on. You have labels, but the labels are ordered. How can you do? Well, first of all, you encode them, giving just the number representing the order. So first label 1, second label 2, and so on. And then you one-hot encode them. What does it mean, one-hot encoding? Is a technique that takes your labels and picks one at a time and transform it into a singular variable, a binary one, which is just 0 or 1. So we are talking about Monday, okay? It just goes to your variables. See how many examples do they have Monday? Okay, all these examples will be 1, and all the others will be 0. And this is your first one-hot encoded variable. Then it will go to Tuesday and do the same, Wednesday and do the same. Everyone will be mapped into 1 and 0s, representing the different categories. And don't worry, scikit-learn can do that for you automatically. One-hot encoder is another function with all the methods that can help you just transform all your data. When you have low cardinality, your approach is quite similar. Low cardinality means that you have a variable with labels, for example, red, green, blue, and they are in a reasonable bound. So let's say from 2 to 255 or even less. And what do? You just one encode. Of course, you don't have here any ordinality, any order to preserve. So just one encoding is enough. One thing that I didn't write here, but should be clear, sometimes you have variables telling you yes or no. If you have a statistical education, okay, you will figure out, oh, it's a dichotomy, an indicator. I will just put just one variable, 1 and 0, and everything is fine. No, actually it's not. If you are working with neural networks, you have to put all your labels. So if it is just yes or no, you have to make one variable for yes, one variable for no. Why? Because if you just leave the no at 0 value, your network will struggle to find out rules when that value is no, because 0 means no signal for a neural network. And here is the big problem. What if you have high cardinality? What does it mean? Okay, you go to a database and you start looking at the variables and you find profession. And profession has a lot of entries. There are many professions. Okay, maybe you say I want to one out encode them, but 1,000, too many. And you go and see the localization of your customers. So you have a town, there are many towns, many cities, and you want to see the address, so on. Use the postal code. There are really so many. How can you do? Let's one out encode. Okay, that's a big problem, because you start having so many variables that you have that sparse data that we said neural network will struggle to find a meaning. So the solution is encode them, transform all your categories into a space, an Euclidean space where you have a limited number of dimensions, but where the coordinates will be the same for very similar labels. For example, you have different selling patterns, one in the northeast of Italy, one in the northwest of Italy, one in the center, one in the south. But you don't have this very good classification, you just have the towns. You put everything inside this approach, which is encoding, and all the towns will be magically just put together into this space, and they are near because of their spatial nearness, even if you didn't provide any information about the space. That's fantastic, right? Okay, it's called embedding. There's a paper explaining about it, and basically, how can you achieve that? First of all, you have to use a scikit-learn function, which is label encoder. Label encoder is very easy. It just picks your labels, which are most often strings, and just transform them into numbers. You just have them numbered, 1, 2, 3, 4, 5, no order, but they become numbers. And then you use an embedding layer, which is exactly what I told you about, and it is a keras, better a TensorFlow keras layer. What does this layer does? It's a matrix. It's a matrix. This matrix just puts as inputs all your information, which should be numbered and numbered. So it means that you really have to count how many labels you have, and you have to make a dictionary of them, because actually this layer one hot encode everything. And then as an output, we have a lower dimensionality space. This is up to you. Usually you take the logarithm of the number of your initial number of labels, or you can try anything you like. You just reduce and see if the reduction is very meaningful for the neural network. Let's see a practical example. So let's say that you start from text and you have variables like this. So you see just an ID. You actually have 24 IDs, but not very realistic, but it's just for making things easier. And this is encoded as 3. And what happens inside this embedding layer provided by TensorFlow? Everything becomes a one-hot encoding vector, which is actually, you see, a vectors made of 24 positions, because you have 24 labels, and the label number 3 has a 1 on it. All the others are zeros. And this enters as input into this matrix. It's a matrix multiplication, and This matrix has many weights. At the beginning, you have to imagine they are all random, but inside the neural network, this provides you an output. Since a matrix multiplication, you have this vector by this matrix, and the result is size 4 as you desire, but you can put any number you want, and this enters inside the neural network and arrives at the end and is evaluated, and by optimization called backpropagation, there's a feedback and the weights will adjust in order to represent exactly what you expect, a meaningful space where your labels are each one positioned into the right coordinates. Is it useful? Yes, it is. Actually, we have companies such as Pinterest or Instacart that use this kind of approach quite effectively. Pinterest uses that in order to figure out the different pins if they are similar or not. By using patterns of people liking or sticking them to their boards, they can figure out if an image is very similar to another one without actually having to decipher by a neural network or something else this kind of information. And Instacart just clusters in this way, but means put together consumers. So if you start buying stuff on Instacart, they can position you in this embedding space, and they can figure out that you are very similar to a lot of other consumers, so they can propose to you to buy certain products instead of others. And you can see that actually it's very easy to just create an embedded layers, and also easy to get out the weights, because once your neural network is trained, you can save everything and reuse them. You can use them for this problem, but also sometimes for other problems. It's very efficient. It's the idea of having a pre-trained. You create your own pre-trained that you cannot find on Google, for example. And maybe you're saying, okay, that's very cool, but how can it work if our labels are dirty? Because, you know, we are working on operational databases. People are just putting inside the information, and sometimes they write things in a different ways or in a wrong way. We put mistakes. It happens all the time. Actually, you can use a technique called dirty encoding. Actually, has been recently formalized by Gal Barocco, one of the most important maintainers of scikit-learn, into a paper. How does it work? Well, you don't put the label themselves, but you put sequences made of small clusters of 2, 3, 4, or 5. You have to find your solution, but 3 is the most effective parts of your label. So, for example, we have here Pfeiffer, and in our database we find Pfeiffer Inc. and Pfeiffer LCC. And basically, if we want to encode or use just our encoding layer and keep them separate as labels, maybe they hand near, but maybe not. It really depends on the quality of information that you can find inside the database. So how can you do? You just split them into shingles, that is small clusters of a few letters, just windowing. And since a great deal of both these is common, is near, that means that into an embedded layer we will just for sure position themselves near in the space. And so basically you have an automatic way to translate all the information you otherwise have to correct by hand automatically into this space. And they are processing the best way possible for a neural network. It's not difficult to do that. Again, scikit-learn use count vectorizer. It has an analyzer called char, which exactly does that. Unfortunately, scikit-learn is done for already providing you a matrix, but TensorFlow and the embedded layer doesn't want a matrix as input. It wants a sequence of numbers, because the numbers correspond to the dictionary he expects to elaborate. So you have to reconvert them, and I prepare for you a very simple function called non-zero by row, which will just translate that for you, that's all. But basically is already done by scikit-learn. And we arrived at this point after, crossing all the spectrum of data inputs to cross-validation. And maybe you're asking, why? Is it not already finished? Why don't we have a look at the possible neural networks architectures? Why are you talking us about cross-validation? We don't see that in deep learning examples. Usually people just take the training set and they just split. They take 80% for training, 20% for validation. And so they can have a good response if everything they are doing is good or not. Actually, when you're working with tabular data, you have less data. You can just do the 80-20 split if you have millions of images and be sure that everything works fine. But most often you are just modeling very complex distributions, and you have very few examples. Cross-validation can give you the opportunity to figure out if what you are doing works or not, because it doesn't split 80-20, but you provide a number called number of faults, usually it's 5 or 10, and you split into 5 or 10 parts your data. By doing so, you can do that. You can use some parts of your data at a time for training and one part left out for validation. And then repeat the same procedure again. And for how many times? For how many faults you created. Because the principle is that one of the faults always stays out. You will have a sequence of results, and these results you just average, take the standard deviation, and we will provide you information is what you are doing is good or not. Please do that. Don't do just the test, the train test split, because it can trick you into choosing the wrong architecture or wrong parameters. Remember, deep neural networks are very cool, they are very powerful, but they have a lot of knobs and levers. They are more complex than a linear regression, more complex than a support vector machine, no matter what kernel you're using. So you have really to pay attention what you are doing. Is it difficult to use it? Not at all. Scikit-learn provides to you exactly the function you need, and it's k-fold. K-fold automatically is an iterator and can give you the indexes you can use for testing your neural network. You have different flavors. I don't stop here now because I think the time is just running out, but you have many choices for sampling correctly your faults and having the good results you expect. So finally we arrive at neural architectures. And last but not least, remember, when you are finally building, so you have your pipeline, you correctly set your experiment by cross-validation, and now you are using TensorFlow for building your architecture, remember, start small. It's not the same principle when you are analyzing images. In images and other problems when you have a lot of data and data is very dense, okay, you start with overcapacity. You make your network as large as possible, and then you try to regularize it, for example, using dropout. It is different. Start small. Use first a small layer. Use linear activation. I know it's a linear regression, but it can help you figure out if what you have done up to now is working and what are the possible results. Then try to add non-linearity. You try to add activation like the ReLU, the leaky ReLU, ELU, CeLU, or JLU. Okay, they seems like keywords, but actually each of these can transform your data into more significant information for a network. I will provide to you some hints about using CeLU and JLU, but we'll talk a little bit later about that. And then you have to try to stack more layers. You start with 1, then 2, 3, even more. And then we find out that actually the activation you decided for before is really determining that, because if you want to stack more and more layers, only the CeLU and the JLU will give you the good signal through all these layers, even if your data is not enough. Then you have to filter data by batch normalization. Batch normalization, what's that? It's a layer that reads your data, arriving in batches, and figures out the mean and standard deviation, and actually does a standardization on the field inside your neural network. Why? Because passing through layers, your data can transform, can become something else, and actually you have to maintain it as possibly as you can with 0 mean and a very small standard deviation. And then use dropout, that means you have to cancel by this layer randomly a certain number of connections. So it's like creating many different networks inside one, and this can help you if you provided too many data or if you provided data which is multicollinear. We didn't explicitly talk of that, but one of the big problems with machine learning, classical one, is data which actually bears the same amount of information. They have high correlation, they are multicollinear because many variables they just correlate together. By dropout, you can just have your network less affected by that and work better. And finally, my suggestion is embed everything into a function. And we show to you an example. This is a Kaggle competition. Kaggle was that. Is a website where you can take data science competitions. Some time ago, there has been one very interesting from Amazon. Amazon has a basic problem. They have a very large organization, many people, many resources. But if you are working for Amazon, you cannot see all the resources. You cannot see all the data, all the tables, use all the software. You have to ask for permission, and permission is long because you have to inquire some people, they have to evaluate your case and provide to you after a while some access token in order for you to use the resource. They wanted to automatize that using machine learning. So they provided a very interesting data set which actually contained all numeric labels. So it was a completely categorical database. And you had categories in the order of thousands, even 30, 40,000. So it was very challenging because you had, for example, encoded all the ID codes of people working in Amazon at different levels. And that meant that you couldn't do easily with very basic algorithms like logistic regression anything good. There's a solution actually using gradient boosting models, but here in this link you can find the solution I proposed to you, and it's working very good, using deep neural networks. Is basically comparable to any other solution by classical machine learning. And you have a function, and the function just takes as input the numeric variables. You just have the names, categorical variables, categorical counts. You have some information about the architecture, so the dropout at different stages, what you're going to use. And here it uses just 2 layers, so how many nodes in each layer. And of course, the dropout, finally, for also the layers, not just the feature input. And it basically, you see the different streams. Here you can see the numerical inputs. So you have an input layer, you have batch normalization, which can transform your data in case you put inside anything strange. And then you have dropout. So we just randomly select some of your variables for your model. And that's all for the numeric ones. You have the categorical inputs instead, and you have 2 lists, and what you put inside your list, first your input, so categorical inputs, and then you put your embeddings, this TensorFlow layer, which actually just needs for you to figure out the number of labels you are providing, the number of dimensions you want as output, and then you put the name, and that's all. You concatenate everything because if you notice it, since it's a list, it means that each categorical variable is dealt as a single input. So your numerical variables will just enter as a single matrix, but your numerical ones will just enter each one at a time, and each one have a specific embedding layer, and that's all. You concatenate everything. You pass everything by 2 dense layers, and you have a dropout among them, and that's all. Very simple architecture. 256 nodes each, and the result is, okay, you use gradient boosting, which is the state of the art, and there is a actual implementation of gradient boosting called CatBoost, made by Yandex, a Russian company, and is very good is achieves 0.876 ROC-OC. ROC-OC is kind of measure that gives you the order. So I want, for example, to have more precision, more recall, as stated in the previous talk about machine learning. Okay, if I have a good error score, it means I can, decide if to have more precision or more recall easily. And if we are going to use instead our solution, what is the result? Is 0.863, which is very near and is very competitive to the previous solution. But the most important thing that I want you to notice is this. If you take the gradient boosted solution, you take the deep learning solution, and you just blend them, you average them, you obtain even a better solution, because they have different approaches, different ways to look at the data, and they can catch different patterns. And so you can have 0.882 as a result. Pro tip, here I explain about the activation, but we skip them because they are a little bit technical, but you can find everything, especially the GELU, the Gaussian error linear unit, which is actually the activation function used in BERT, the state-of-the-art neural network for text. And we arrive at a conclusion because I know it's almost lunchtime and don't want to just run over the time. I also give you an opportunity to make some questions. Wrap up. So, can we use deep neural network for tabular data? Yes, we can. We are an alternative solution compared to classical machine learning approaches. They require ad hoc architecture, so there is really no pre-compiled solution for you, but actually you can craft them very easily using a combination of TensorFlow and scikit-learn. This is very important. And then you have a very important takeaway, which is the entity embeddings. The embeddings can not only help you to handle categorical data, but can provide to you a kind of Rosetta Stone for every situation where you have similar data and you want to process them by neural networks or other algorithms. And they can use also for cluster analysis. Most of the time, okay, gradient boosting is still quite easy to use and quite efficient in providing a solution. But deep neural networks is getting very near. The solution you can get by TensorFlow will be very competitive. And remember, even if they are not, you just take a solution by a classical machine learning algorithm, you just blend it with a deep neural network solution, and you will get a completely different performance, always better. And this is the very important takeaway I want you to remember. So, thank you, and I leave you at this time the word for any question you have about my presentation.